Welcome to the camera section of the course, and in this section we'll be covering everything camera related in V-Ray. And if you have a photographic background, this section should be a piece of cake for you, as every concept here is based on a real world situation. In this particular lesson we'll be covering physical camera. V-Ray had its own physical camera for a long time, but from 3ds Max 2016 there is a 3ds Max physical camera that is fully compatible with V-Ray, and it actually was co-developed by Autodesk and Kiosk Group. And now 3ds Max physical camera is the main camera you use to render your scenes in V-Ray. But if you open up an older scene that was utilizing V-Ray physical camera, you would have no problem, and there is actually a way to create the old V-Ray physical camera if you fancy that. But for now, let's focus on 3ds Max physical camera. You can add a physical camera from the V-Ray toolbar, command panel, or the menus. I tend to use V-Ray toolbar to add the camera. So let's click on this physical camera icon in the toolbar and click and drag in the viewport to add a new camera. Now press Ctrl C so the camera adheres to the current perspective view. We are still in the perspective view, so press C to view the scene through the new physical camera. Now as you can see, a new physical camera has been added to our scene. Select the camera and go to the modify panel and see what we have here. In the basic rollout, the first option we have is targeted, which is enabled by default, and in this case if I change the view to a quad view, you can see the camera has a target object. We can select the target in the Explorer and move and transfer our camera around, and if we disable it, the camera would be a free camera. Next we have target distance, which basically sets the distance between the camera and the target or focal plane. And if we take a look at the focus section right now, the focus point or focal plane of our camera is based on the target distance. Let's say I want the focal plane of the camera to be on this chair here, possibly something like 500, maybe 35 centimeters would be enough. In the viewport display section, we can decide when we want to see the camera's cone in the viewport. By default, it's set to when selected, so only when the camera is selected the camera's cone will be visible. If set to always, it will always be visible whether the camera is selected or not, and if set to never, it will never be visible. Let's set it to when selected. We have show horizon line, and if I hide all my geometries and enable show horizon line, we get a black line which represents the horizon line in the scene. It can be useful sometimes. Let me disable it and unhide all the objects in the scene. In the physical camera rollout and in the film and sensor section, first we have preset, and here you can define your film or sensor size, and we got full frame, APS-C Canon, APS-C Nikon, APS-C H, 4/3, and custom, where you can set the sensor size manually down here using the width parameter. In a digital camera, sensor is the very heart of your camera. It determines the final resolution of your image, its size, how good your camera performs in low light situations, the dynamic range of your photo, and obviously the larger the sensor, the better the quality of your photo, and full frame sensor is the largest sensor. But in CGI it really doesn't matter that much. Maybe if you are trying to match your camera to a live action camera or a photographic plate, this option can be very useful. I mean, sensor size is extremely important, and possibly the first thing you look for if you are buying a new camera. For example, you're gonna get much shallower depth of field if you are using a full frame camera like Canon 5D Mark III compared to a 4/3 camera like Panasonic GH4. But here the sensor size is not as important as real life. In the lens section we have focal length, which is the focal length of the lens, And basically focal length determines the angle of view, how much of our 3D scene will be visible in the render, basically the overall magnification. The longest or higher the focal length value, the narrower the angle of view, and the higher the magnification. And the shorter the focal length, the wider the angle of view and the lower the magnification. So if we start from a short focal length like a 10mm lens, you see we have a very wide angle of view, and as I make the focal length longer, we would have a narrower angle of view and higher magnification. Let's try 18, 24, 55, 85, 135, and 200. Let's use 18mm for now. Next we have specify field of view. When on, lets you set a new field of view value in degrees and allows you to control your focal length in degrees, which might be easier for some people. So if we want to achieve longer focal length, we can use narrower angles and vice versa. And as I'm changing the angle here, you can see the focal length is getting updated. So while specify field of view is on, the focal length control is disabled. However, changing the value of one of these controls also changes the value of the other. Let's disable specify field of view and set the focal length to 80 for now. Zoom basically zooms the lens in or out without changing the camera's position. This option provides a way to crop the rendered image without altering any other camera effects. I mean, if I set the zoom factor to 2, we are going to have the same field of view as setting the focal length to 160mm. But changing the focal length changes the depth of field effect because it changes the aperture size, while changing the zoom value does not. So if we increase our focal length to 160, the depth of field will be shallower, but if we increase the zoom factor to 2 to get the same result, the depth of field will be the same as before. Next we have aperture, which sets the size of the lens aperture as an f number or f-stop. The f-stop changes the aperture of the lens. A smaller f-stop number like 2 means the aperture is more open. A higher f-stop number like 16 means the aperture is more closed. F-stop affects two things. First, exposure, and second, how shallow or wide depth of field effect is. We are gonna be talking about depth of field in our next lesson, but for now we are only focused on how the f number affects the exposure. A smaller f-stop number means the aperture is more open, therefore more light is gonna reach the sensor and the overall image is gonna be brighter. And a higher f-stop number means the aperture is more closed, so less light is reaching the sensor and therefore darker overall image. Right now, because in the exposure rollout, the exposure method is set to target, which we'll be discussing in a moment, f number doesn't affect the exposure. It only affects the depth of field and how narrow or wide it is. For now, let's set the exposure to manual. Now f-stop, shutter speed, and ISO control the overall exposure. Let's take a look at a few renders with different f numbers. In the first render, f-stop was 1.4, and because the aperture is wide open and more light reaches the sensor, we get a very bright and overexposed scene. In the next render, f-stop was 2.8, then 5.6, then 8, 11, and 16. As we can see, by increasing the f number and closing the aperture more, each time we get darker and darker renders. In this case, f-stop of 8 results in a well exposed image, I guess. So let's make sure f number is set to 8. Using the focus section, you can define distance for the camera. By default, it's based on the target distance, which we discussed earlier, or you can set it to custom and define your own focus distance manually. Lens breathing adjusts the field of view by moving the lens toward or away from the focus distance. A lens breathing value of 0 disables this effect. And we have enable depth of field, which allows you to enable or disable depth of field effect. We'll be discussing depth of field in detail in our next lesson. For now, let's continue with the rest of the parameters. We have shutter or shutter speed section. The shutter is a light occluding piece of metal in front of the camera sensor to block light from reaching the sensor all the time. When you take the photo, the shutter is moved out of the way to expose the sensor to the light. Then it is moved back again in front of the sensor. The speed at which this is done is shutter speed. The faster it is, the shorter time the sensor is exposed to light. So if you have dark interior scene, for example, you need to use a long exposure or longer shutter to avoid an underexposed render. But for a daylight scene, you need a much shorter shutter speed to avoid an overexposed render. Shutter speed also controls motion blur, which we discussed in its own lesson. In the shutter section, first we have type, and here you can define which unit to use in measuring shutter speed. We have frames, which is typically used in computer graphics, second or fractional seconds, which are typically used in still photography, or degrees, which are typically used in videography. I personally tend to use fractional seconds, so let's use that. And we have duration, which sets the shutter speed, basically how long the shutter would be open. Let's take a look at a few renders with different shutter speed durations. The first render was done with the shutter speed set to 5,000th of a second, and because shutter is open for such a short time, the render is underexposed and very dark. In the next one, shutter speed was 1,000th of a second. The shutter was open longer, so the sensor was exposed more to light, and we get a brighter image compared to the first one. Then it was 100th of a second, then 50th of a second, and finally 10th of a second. In the last render, because the shutter is open for such a long time, we get an overexposed render. In this case, the render with shutter speed of 50th of a second is well exposed, so let's set the duration to 50th of a second. So up to now, we know that when the exposure gain is set to manual, both aperture and shutter speed affects the exposure of the render. And as we'll learn in a moment, ISO also affects the exposure in this mode. In the shutter section, we have offset. It specifies when the shutter opens relative to the start of each frame, and it affects motion blur, which we will be discussing in its own specific lesson. And finally, we can enable or disable motion blur, which, as I mentioned, will be discussed in detail in a later lesson. In the exposure rollout, first we have install exposure control button. If enabled, by clicking it, it would make the physical camera exposure control the active exposure control in the scene. But if it is already active, the button will be grayed out like now and reads exposure control installed. In the exposure gain section, we have two modes to control the overall exposure. In the manual mode, the exposure is dependent on aperture size, shutter speed, and the ISO value here. But in the target mode, which we'll learn about it in a moment, only this single exposure value here is responsible for the overall exposure, and aperture and shutter speed control only depth of field and motion blur. ISO is film sensitivity to light. A higher value means more sensitivity, therefore brighter render, and a lower value means less sensitivity, therefore darker image. Now let's try a few render with different ISO values. In the first render, ISO was 100. Then 400, and finally 1600. As we increase the sensitivity, we get brighter images. but controlling the exposure with aperture, shutter speed, and ISO is not very easy. And at the other hand, it's going to cause some limitations when working with depth of field and motion blur at the same time. So that's why we have this target exposure mode. In this mode, the EV, which stands for exposure value, is the only value controlling the exposure. Higher values produce darker or less exposed renders, and lower values produce brighter or more exposed renders. In this mode, the shutter speed, duration, and the aperture size won't affect the exposure at all. They are just responsible for motion blur and depth of field effects. And also, this is a default mode and my preferred exposure mode as well. The proper EV value is different based on the type of the scene you are working with. Something around 10 would be good for a daylight interior render, something from 13 to 15 for a sunny daylight exterior, and something like 6 to 8 for a studio setup would probably work. Now let's try a few exposure values. In the first render, the EV value was set to 6, and as you can see, the render is a bit overexposed. Then it was set to 8, then 10, then 12, then 14, and finally 16. As we can see, by increasing the EV value, the scene gets darker and darker. For this lighting, I think an EV of 10 would probably give the most well exposed render. The rule is very simple here. Each time you decrease the EV value by one stop, let's say from 10 to 9, we double the scene exposure and make it twice as bright as before. And each time we increase the EV by one stop, let's say from 9 to 10, the render gets twice as dark as before. Let's set the exposure value to 10 here. Next we have white balance section or group. Basically the lighting condition and the color of the light sources can affect the color of your objects in the scene. We as human beings can compensate for that and actually see the white objects as white in any lighting condition. But in 3D applications and digital cameras, we need to adjust the white balance so that white objects in the image appear white, and therefore all other colors in the image also display correctly. And also, you can use white balance to add a certain color cast to your render if you want to. We have three ways of setting and adjusting our white balance: illuminant, temperature, and custom. In the illuminance mode, there are some presets based on standard light sources. In the temperature mode, the white balance would be based on a temperature in Kelvin degrees, and in the custom mode, you can choose any color you want to adjust the color balance. By default, it's set to illuminant and it's using daylight preset, which corresponds to 6500 degrees Kelvin. In kelvins or K, the lower the temperature, for example 3200 K, the more red the light will be, and the hotter it is, for example something like 9000 K, the bluer the light will be. Now if you take a look at the presets, you can see, for example, we have incandescent 3200K. Obviously an incandescent light source will cast a very warm reddish light that makes the white colors to look another color in the photo taken by a camera or in your renders. Unless this is something that you want, you can white balance the scene by setting the preset to incandescent 3200K, and by doing so we cast out that warm red color temperature and white balance the scene. If you are in a natural daylight lighting, you can set the preset to a neutral daylight 6500K. If you are under very hot warm sunlight and there is some yellow color cast in the scene, you can use sunlight 5200K preset to make the whites whites again by casting out the yellow color produced by the camera. By the light source. If I go to the frame buffer and load the render with EV set to 10 and also enable my correction tools and enable white balance, If I want to make the scene cooler, we need to cast out some warm tones. So we set the temperature to a hot temperature like 5000 for example. Now the render looks bluer and cooler. And to do the opposite, we just need to set the temperature to a higher one like 8000 to make the scene look warmer and cast out some cooler tones. Now let me show you a few renders with different presets. The first render was done with a Daylight 6500K preset, which is the default preset. The next render was done with Sunlight 5200K. Now we are casting out warmer tones and getting a cooler image. Next one was done with Shade 7000K preset, and now we cast out cooler tone and getting a slightly warmer render. If we take a look at the render with Daylight 6500K, because of the dominant blue sky that we have outside, we get a slightly cooler tone than what we possibly want. But in the shade render, we get a warmer render. And in the final render, Incandescent 3200K was used, and we get this very blue render. We can set the white balance mode to temperature, and instead of using the presets, use any temperature that we want. Let's set the temperature to something like 9500. Now we are going to be getting a warmer render because we are casting out a cool temperature, and you can see the result in the frame buffer. Obviously you can set it to custom and pick any color using the custom option. If I select the daylight render again, I can actually use the white balance correction in the frame buffer and adjust the white balance here. For example, let's make the tone cooler by using a warmer temperature, or vice versa. But doing it here is not going to give you the exact same result from the physical camera. For small adjustments, the white balance correction is quite enough here, and it is a correction, and you don't have to render your scene every time to get the correct white balance. In this case, let's set the white balance to temperature and set the value to 7500K, so we get a warmer render and cast some blue out. Next we have enable vignetting, and it means darkening of image corners when compared to the center. So let's enable it and try a few vignetting amount. In the first render, vignetting amount is set to 0, so no vignetting. Then it was set to 1, 2, 5, and 10. For now, let's set it to 0 and disable it. Another way of achieving vignetting is by using optical vignetting in the bokeh or depth of field rollout. This vignettes the frame by simulating the cat's eye effect that some wide-angle lenses can generate. For this to work properly, we need to have depth of field enabled. We're going to be learning more about this effect and depth of field in our next lesson. Bokeh or depth of field rollout will be discussed in the next lesson, obviously. Next we have perspective control rollout. These settings shift the camera view horizontally or vertically without rotating or tilting the camera in both the X and Y axis. We can use positive and negative values here to shift our camera without tilting or rotating the actual camera, which can be useful. In the tilt correction group, you can tilt the camera horizontally or vertically to correct the perspective, particularly in scenes where the camera is already tilting up or down, and to achieve the simulation of tilt lenses for 2-point perspectives. Also, auto vertical tilt correction. When this is enabled, vertical value will be set automatically to align perspective along the z-axis, and it is very useful in exterior architectural visualizations to correct the perspective. In the lens distortion rollout, you can control the lens distortion of the camera. When set to none, no distortion is applied. Next we have cubic distortion. Positive values introduce pincushion distortion. Negative values introduce barrel distortion. In pincushion distortion, the greater the distance from the center of the image, the more lines warp inward toward the center. Pincushion distortion also vignettes the image to a level. In barrel distortion, the greater the distance from the center of the image, the more lines warp away from it. In the first render, distortion amount was set to 0.1 and we get the pincushion distortion type. As I'm using positive and negative values, you can see in the viewport this blue grid, which is from our camera, represents the amount and type of the distortion. But we cannot see the actual distorted image in the viewport. So let's see a few render with pincushion and barrel distortions. So as I said, the first render was done with distortion set to 0.1. The next one, it was 0.2. As you can see, we get stronger pincushion distortion. And finally 0.3. Then to see the barrel distortion, I started using negative values. First negative 0.1, then negative 0.2, and finally negative 0.3. Let's set the amount to 0 for now. Also, you can use a texture to distort the image. For now, let's set the distortion to none. In the miscellaneous rollout, we have clipping plane section. Using this section, you can clip or hide certain parts of your objects from the render view while still having them affect the lighting in the scene. When this parameter is active, two planes are attached to the camera, a near and a far plane. Anything before the near plane will be made invisible in the render, and anything beyond the far plane will be made visible in the render. So only the things that are between the near and the far plane will be visible. Let's try 500 for the near plane, maybe 550, 650. As you can see, anything in this distance from the camera is clipped away. And if I set the far clip to, let's say, 700 centimeters, you can see only the parts of the objects that are between 650 and 700 centimeters are visible, and the rest is gone. Let's set the values to 0 and 100,000 centimeters and disable clipping. In the environment ranges group, we have near and far range, and these determine the near and far range limits for the atmospheric effects set on the environment panel. Objects between the two limits fade between the far and near values. And in the V-Ray properties section, we can define the resolution of the bokeh texture, which we discuss in the next lesson, and in the lens distortion group, which allows you to load a .vr lens file generated in the lens analysis utility, which is provided with V-Ray, and you can find this tool in the tools folder of the V-Ray installation folder, and you can use this file to distort your image. Now let me, for the final render, enable vignetting and set it to 2, and we can take a look at the final render. As always, right click on the image and choose load render settings to see the final render settings that I've used for this render. Also, we have a denoiser pass as well. Now we can enable our correction controls and adjust the overall exposure of the render if you want to. Or adjust the white balance. Okay, in this lesson we learned about physical camera. I will see you in the next lesson for the depth of field discussion.